Hello everybody, we are in week 6 of this particular course. In today's class, we shall look at magnitude comparator, and before that we shall have a quick review of what we discussed in week 5. If you remember, we discussed number system and the representation of numbers in binary, and the code that we arrived at were weighted codes, in the sense that every place has got certain weight associated with it. When it is binary, before the binary point we had weights like 1, 2, 4, 8, 16, so on and so forth, and after the binary point it was half, 1 upon 4, 1 upon 8, 1 upon 16, so on and so forth. Okay. And to convert decimal to binary, the integer part was successively divided by 2 and remainders were accumulated, and for the fractional part, coming after the binary decimal point, it was successfully multiplied by 2 and the carry was accumulated. And we had seen that fixed point arithmetic has fixed precision and it follows integer arithmetic. And for negative number representation, sign magnitude was discussed, and also 2's complement, 1's complement, all those things were there, and then we discussed 2's complement arithmetic. And then to design circuits for adder addition and subtraction, we saw ripple curry addition and how we can convert a ripple curry adder to a subtractor. Okay. And then we discussed carry look ahead adder for first addition, where the carry generation process was converted to parallel from serial by unlooping the iterative equation. And then we discussed overflow detection, how to detect overflow if the number goes out of the range. And then we also discussed BCD addition and the logic behind it, how to arrive at those logics. So, as I said, in today's class we shall discuss magnitude comparison. So, magnitude to be compared is between two numbers, and the numbers, whenever we talk about comparison, then the first thing that occurs to our mind, why don't we subtract one number from the other, say one number is x, another number is say y. So, if x minus y is 0, then it is equal, the numbers are equal. And if x minus y is positive, the number is x is greater than y. If x minus y is negative, then the number is x is less than y. Okay. This is the thing that will occur to us, and of course we can get a magnitude comparison done by subtraction process. Okay. So, that we can do, and for that we can have a subtractor circuit developed from 2's complement by using 2's complement arithmetic and a full adder circuit. So, in that, the way we have seen it before, how the subtraction works using 2's complement arithmetic. So, when x is equal to y and x greater than y, we see that carry out generated is 1. Okay. So, you have to refer back to the 2's complement arithmetic by which the subtraction is done. Those examples, the study that we had done in the previous class. From there, we take the important point that if x is equal to y and x greater than y, then carry out that is generated is equal to 1. And if carry out generated is 0, then the number is negative, that is x less than y. I mean the result is negative, so x is less than y. Okay. You remember that? Okay. Then from that we can get the logic for x less than y very clear, easily, that if the carry out is 0, no carry is generated, then the result is x less than y. So, in this case we can the corresponding output, say x less than y, we can directly get from C out prime complement of the carry out. Okay. And when carry is generated, then there are two possibilities, one is x is equal to y, another is x greater than y, right. So, x is equal to y will occur when all these sum bits are 0, right. So, at that time we can follow this particular logic that all the each of the sum bits are 0, no digit is 1. So, that means that the numbers are equal, result is 0 and carry out generated is 1. Okay? That is following 2's complement subtraction. And if any of the sum bit is 1, so that follows OR logic, by which we can AND it with C out. Okay, the carry is already generated, so that gives you x greater than y logic. Okay, so this is the basic idea. And of course, when you are generating multiple output function, we can see that whether output of one can be used, I mean some intermediate output can be used in two different places. So, accordingly certain minimization you can think of, otherwise the basic logic remains this what we have arrived at. Okay. So, but when we look at magnitude comparison and our objective is to generate only x greater than y, x is equal to y and x less than y, we do not actually need the subtraction result, that is S3, S2, S1, S0. Okay. So, we are doing more than what is expected from us in terms of magnitude comparison of two numbers, isn't it? So, can we have a can we use less hardware, another kind of circuit by which we generate only the result that compares two numbers. Okay. So, we will go for 4-bit number comparison the way we had seen before, or larger number of bits. So, we begin with 1-bit magnitude comparison. So, two numbers are of 1 bit. Okay. So, if x and y are of 1 bit, so the number possible, the possible combinations, the way we can compare them when x is equal to 0, y is equal to 0, x is equal to 1, x is equal to 0, y is equal to 1, x is equal to 1, y is equal to 0 and x is equal to 1 and y is equal to 1. So, these are the 4 possibilities by which you can do the comparison. And in this case, you can see that 0, 0, x and y both are 0, that means x is equal to y. So, this will be 1, neither x greater than y nor x less than y. So, they are 0 and 0, clear. So, x is equal to 0 and y is equal to 1. Of course, y is more and x is less. So, x is less than y, that is equal to 1 and rest 2 are 0. X is equal to 1 and y is equal to 0. So, x greater than y is 1 and when both of them are 1, again they are equal. So, other 2 are 0. Is it fine? So, by this we can figure out that x greater than y is occurring for this combination. So, we can get it by x y prime. So, g we are giving g for greater than x greater than y. Okay. And then x less than y, right, that is occurring for this particular case. So, that is x prime y, x is equal to 0 and y is equal to 1, clear. And finally, x is equal to y is occurring for these two cases, the other two cases, that is this one and this one. So, this is x and y both 0. So, that is x prime y prime and x and y both 1. So, x y. So, you add them up, sum them up, you get the final expression. So, these are the the basic logic by which you can get 1-bit comparison done. Okay, you do not need to do other things. Okay. Now, since we are generating x y prime and x prime y, right, do we need to additionally generate x prime y prime x y, so that means 2 other AND gates and then add it up, okay, or we can make use of this and see whether another gate, not more than one gate is required to get the final x is equal to y output generated. Okay. So, that we can investigate. So, for that we can see that x prime y prime OR with x y, we can write this as x prime OR y and AND with x or y prime. You can see that x prime and x will become 0. So, x prime y prime will come from this particular term first this thing, and y x will be there from this 2, and y prime will be 0. Okay. So, once it is there, then this particular term x prime y prime from De Morgan's theorem we can write in this manner, and this one also in this manner. And finally, so we have got our x y prime and x prime y. Okay. And then again we apply on this particular term De Morgan's theorem, so you can get a NOR relationship. So, a NOR of these two term which is already generated or need to be generated, we get x is equal to y logic. Okay. We do not need to generate separately these two. Okay. And the other thing that we can see, that we can generate this x y prime and x prime y by NOT gate and then ANDing, which is possible. Okay. If already in some cases you are generating x inverse of x complement somewhere or y complement, you can make use of it or you can generate it. But otherwise also we can see that if we have a NAND gate between x and y, we are getting x y NAND, which is nothing but x prime plus y prime. Okay. So, when you AND x with that, so x prime will become 0. So, x y prime will be generated here, and if you AND y with that, right, with this one, so x prime will be generated and y prime will become 0. So, we can get generated this one. Okay. You do not need then one and additional those two NOT gates, rather one NAND gate will do. So, by this we can get this made. Clear? So, that is for 1 bit comparison. Now, let us look at how to do 2 bit comparison, right. So, for 2 bit comparison, then the number we are having is x1 x0 and y1 y0. So, x1 is the more significant bit and x0 is the less significant bit, accordingly it is for y. Okay. Now, we know that x as a whole, the number will be greater than y if x1 is greater than y1, isn't it, more significant bit. So, if x1 is more than y1, what is the option then? That means x1 is 1 and y1 is 0. Then irrespective of the rest of the bits 0 0, 0 1, 1 0, 1 1, all the time, right, you are having x greater than y for all these cases. So, this is your x1 and this is your x0 and y0, okay, and this is your y1 and this is your y0, right, because more significant bit is larger than this. Okay. So, in this case you do not need to worry about the other things. Okay. So, when x1 is equal to y1, that both of them are 0 or both of them are 1, then whether x is greater than y or not is decided by the x0 y0 comparison, right. So, this is at that time only you look at it. So, this is we know between comparison of two numbers. So, basically we are looking whether x1 is greater than y1 and also we are looking at x0 is greater than y0 when x1 is equal to y1. Now, if we remember the way we had compared 1 bit generation. So, x1 greater than y1 we can get if we do 1 bit comparison of x1 and y1. Whether x1 is equal to y1 we can get by 1 bit comparison of again x1 and y1, where the equality part is looked at, x is equal to y output is looked at, and x0 y0 will come from 1 bit comparison of the lower significant bit x0 and y0. So, what we do, we generate two 1 bit comparator, we use two 1 bit comparator, right. So, one is to generate G0, E0, L0 by the same equation that we had done before, and another is for G1, E1 and L1. Okay. And so, we write, so basically this is the generic 1 bit comparison circuit. So, instead of x and y we are writing xi, yi to indicate the bit position. So, 0th position position 1 and position 2 also. Okay. Is it clear? So, this is the way circuit is made. Now, if we look at this x greater than y thing, so x1 greater than y1 is your G1, it will be given by G1, right. So, if G1 is high, G1 is true, then x will be greater than y irrespective of the other things, right. When G1 is not high, right, then two possibilities are there, that the number is equal or number x1 is less. So, if the number is equal E1, then you look at whether the lower significant bit G0 is high, or not, lower significant of x is more than y or not. Okay. So, this way you get the logic for x greater than y. So, similar thing we will get for x less than y, where we will look at L1, if x the higher significant bit is lower, of course, it will be less, and if they are equal, then we will look at the next significant bit, lower significant bit, whether it is less, then it will be as a whole the number will be less. And when it will be equal, when both E1 and E0 are equal, then only it will be equal. Is it okay? So, 2 1-bit comparator and additional logic circuit will give me 2-bit comparison. Okay. Now, if we extend it, we can get n-bit comparison, which includes 4-bit comparison, the way we have seen subtraction and all of 2 4-bit numbers before. Okay. So, in this case, x greater than y, and the numbers are x naught to x n minus 1 and y naught to y n minus 1, and we are looking at as a whole x greater than y or equal to y or less than y or not. Okay. So, we will be having n number of 1-bit comparison circuit the way we have seen before, right. And then we look at the most significant bit first, g n minus 1. If this is high, then of course x greater than y, right. If it is not high, low, then if the most significant bit is equal, if it is less than the most significant bit of x is less than, then you do not need to go to next step. If they are equal, okay, then you look at the next significant bit. If the next significant bit is also equal, that is E n minus 1 ANDed with E n minus 2. So, that tells that both the most significant bit and next most significant bit, they are equal. Then you look at the next significant bit, okay, whether that is more than the other or not. Basically, we are talking about in this case say 0 0, this is also 0 0, this is x and this is y, right. So, both are equal, then you are looking at whether x this particular position is more than this or not, okay. Or the other case, that when both are 1, right, then whether this is 1 or not. So, this is where you are when you are discussing, we are looking at this case. So, if they are again equal, if you see that they are equal, so it could be 0 0, could be 1 1, then you look at the next case, whether this is 1 or this is 0. So, this is the way the equation can be understood, right. X is equal to y will come in this manner, and x less than y will look at the where this ln minus 1, en minus 1, ln minus 2. So, this is similar to the other case, okay, greater than case. Is it okay? Now, when you develop the n-bit circuit, maybe a 4-bit comparator, which we shall see later. So, it might so require that you are looking for 8-bit comparison, okay, but you have got a 4-bit comparator IC or 4-bit comparator circuit available with you. So, you would like to cascade it, you would like to connect to another IC, isn't it? So, that is what your intention will be. So, in that case, you need to have option for connecting inputs, okay. So, in this case, when you do that, we do it this way, that the input is coming from lower significant bits. So, current IC is current circuit is comparing the more significant bits. So what we will do? So everything is remaining same. When all current one are equal, more significant bits are equal, then you look at whether x is greater than y, that is coming from the lower stage, lower significant bits. So x greater than y in or not. Okay. And if all are equal, if x is equal to y in is equal, then as a whole it will be equal, right? And similarly for the less than cases. So now we are putting a out and in prefix in these cases, because we are now in a position to accept output of comparison from lower significant bits from another logic circuit. Okay. Now we come to a 4-bit comparator IC, which is used in practice, right? And so this is IC 7401, IC 7485, and you can see what is there. This is a 4-bit comparator IC. Okay. So these are the X 4 bits and these are the Y 4 bits. These are the inputs that I said can come from lower significant bits, where the lower significant bits are getting compared in another IC or another circuit, and these are the output of this stage, okay, which also considers the input, right? And if you look at the circuit, these are all these blocks are 1-bit comparator, you can see over here, right? And we have used these bubbles not option, so we can just compare and see. For example, this particular AND output is 1 when A3 is equal to 0 and B3 is equal to 1. How is it that? You can see that if A3 is equal to 0, this output will be 1, right, and B3 is equal to 0, right, B3 is equal to 0, then this is B3 is equal to 1, then this 1 is also coming. So both of them are 1, so this AND gate output will be 1. So this 1, this is 0, so this output will be 1, okay. Sorry, this output will be 0, because this is AND gate, and at the input of it 1, its inverse, so that is 0 is there, okay. So if B3 is more than A3, then this cannot be 1. Similarly, if you look at this particular AND gate, okay, so if A3 is equal to B3, if you look at the connection, A2 is equal to 0, B2 is equal to 1, then this output will be 1. So that also ensures that in that case the output will be 0. So this is the way the circuit has been developed, right? And if you look at the function table of IC 7485, okay, as we had discussed, it is similar if A3 is greater than B3, right, irrespective of what are the other inputs as well as the cascaded inputs, the output will be A greater than B, okay. And if A3 is less than B3, then it will be less than B3, right. And when A3 is equal to B3, at that time you look at whether A2 is greater than B2 or not. If A2 is greater than B2, irrespective of the other cases, A greater than B, okay. So this is follows what the what basic comparator logic should follow, okay. Now comes when all of them are equal, all these current bits. So this is the case, A3, A2, A1, A0 are equal to B3, B2, B1, B0. So at that time, if A greater than B, right, then at the input, then A greater than B at the output. So it is now looking at the lower significant bits, okay, comparison of that. Similarly others, and when A3 is equal to B3, then this is if this is high, then this will be equal to B. Now it is not expected that at the input side, okay, both x greater than y and x less than y both will be equal to 1, because either it is high or it is less, okay. So that is what is expected, right. But in case it happens for some reason, the circuit is made in such a manner, even though it is not expected, that if both of them are high, then the output in this case A greater than B, so both of them are low. If both of them are low, then both of them are high. This is what is there, which we shall see can be used to our benefit in some configuration. Okay. So, this is going to happen in normal cases, but according to the logic circuit that has been developed, this is what the function table gives us. As such, this is a don't care at the input side. Okay. But because this is there in the final truth table, we can see that it can be put to some useful configuration of comparator circuit for larger number of bit comparison, and that part we shall take up in subsequent slides. Now, as I said, it can be used for comparing more number of bits because of the option that is available as input. So, if you look at 8-bit comparison, so of course, the lower significant bits need to be placed here and here. This x is equal to y input is kept high, the others are kept low, x greater than y and x less than y, clear? And so, these outputs x greater than y equal to y and x less than y, whatever is getting generated here in these three cases are fed as input to the next IC, and the final output is taken from here. Okay. Is it clear? Now, if you look for say 24-bit comparison, right, how will you go about? So, you will be requiring 6 such ICs. So, the first case you will be connecting it in this manner, right, that is the input pin number 3, that is x equal to y in, that will be high and other two will be 0. So, for the first one, right, and after that you are connecting the way you have connected it. So, final output will be generated from here, right, and in this case the final output generation will depend on the logic operation done in previous cases. So, basically this comparator will wait till the this previous comparator generates its output, this will wait till this one generates its output. So, that way you see the propagation delay in cumulative in nature. Okay. This comparison result will come, but it will be the delay of each of the stage will get added up, which is how it is going to work. But we can have another configuration where we are using the same 6 comparator only for 24-bit comparison. So, there we can put 5 such comparators here in the first place in one stage, which is giving comparator output after 1 unit delay that happens within the comparator, and after that it is another level. So, it is a 2-level comparison, right, and you see how intelligently the connections has been made. As such, for 5 you can get 5 into 420 inputs, but how 24 inputs have been placed there. So, for this least significant 4 bits are connected the standard way. Okay. So, the A is equal to B is high and the other 2 are low, right. So, there goes 4 inputs, and we have another 20 inputs to place, right. So, that is placed, 5 of them are placed in rest 4 in the first stage, here 5, 5, 5 and 5. How? And then these outputs, okay, are put over here. So, the first one is these 2 and rest these 4 A naught B naught to A3 B3 are coming from rest 4. Okay. So, how does it work? So, in the first place this A4 B4 you are placing it here, and A4 if it is greater than B4, then it is fine, it is A greater than B, it will go in that manner. So, the corresponding output will be generated, right, A greater than B. Otherwise, if B4 is more than A4, so the A less than B will be generated if other bits remaining same, if all of them are remaining same, because this is of lower significance compared to other. Now, if they are equal, all these are same, they are equal, that is where the problem could have been there, right. But if they are equal, we have seen in the previous case in the function table, as I was telling there, if they are equal, you see the outputs are also equal. If both of them are high and both of them are low, output are also LL and HH in this particular case. So both of them will be low or both of them will be high in that case. So when they are fed as A naught B naught here, so both of them are high and both of them low, so they do not contribute to the comparison. That is equal. I mean contribute in the sense that input is equal. So if everything else remains same and the output is depends only on A4 and B4 comparison, so as to say, okay, then if both of them are low or both of them high, will generate same high and low output here, and over here same high and low, and the output will be A is equal to B in the final place. So the fifth bit can be inserted in that here like this. So similarly for the other cases, so 4 into 5 20 and this is 4. Okay. So that is the clever use of this thing, and by which you can see because of the parallelism the propagation delay can be reduced. Okay. So with this we come to the conclusion of this particular discussion on comparator. Magnitude comparison of two numbers can be done by subtracting one number from the other and developing suitable logic circuit to generate this x greater than y, x is equal to y, x less than y outputs. We shall see in the next class the ALU, basically arithmetic logic unit, does it in that manner only. You do not have separate comparator circuit within it. A direct approach for magnitude comparison of two numbers can avoid subtraction. In this place value of the bits being compared is useful. I mean, if it is more significant bit they differ, then we can arrive at the decision from that directly. IC 7485 is a 4-bit comparator with option for connecting input from lower significant bits that are getting compared in another IC 7485 or logic circuit, and delay at every stage can add up for larger number of bit getting compared when you connect them in serial, but there can be an option of parallel multi-level arrangement. Okay. Thank you.